Hi there! Welcome to the 9th episode of the Synth project, where we are going to build a synth together. Last time we talked about 3 of the 6 circuits that need to be added to the basic VCO schematic with the SSI 2130 to basically complement its features. Today we will complete our talk working on the last 3 of those circuits. 2 of them are taken directly from the SSI 2130 datasheet suggestions, and will be included directly in the full schematic. The last of the 3 circuits is something I designed specifically to prevent breaking the 2 auxiliary mixer inputs of the IC. I believe you'll find it very interesting because of its peculiarity. We will go through its schematic and we will also test it in lab to make sure it works as expected. Let's begin. Hi there! I am Carlo Carrano, and this is Electronics Engineering Made Easy. Let's start by talking about the transpose function. If the synth is used with the help of a keyboard and needs to play along with other instruments, it is important to have it attuned to them. And it is also useful to have a transpose function if we want our synth to start making sounds above a certain bass frequency. And I'm sure that you can find many other reasons to have such transpose functionality. It is therefore important to have a way for adjusting the bass frequency that the synth can emit by the means of its exponential input. We can do that by creating a simple circuit that provides voltages in a predefined range, and those voltages can be applied to the exponential input just by adding one extra input identical to J4, J5, and J6. And here is the circuit. It is a very simple voltage divider controlled by a multi-turn potentiometer. The value of the potentiometer and the resistor R1 have been chosen in such a way that the P-expo output, when the cursor is all the way down, is of 0 volts, and it is instead 10 volts when the cursor is all the way up. Since the exponential input is set to provide 1 octave per volt, this 10 volts range will allow us to modify the bass frequency in a range of 10 octaves, or from about 1 Hz up to 1024 Hz. Pretty darn good, isn't it? And because we can go really high with the frequency, I have decided to use one specific suggestion from the datasheet of the SSI 2130, which is a simple circuit that is supposed to adjust the shape of the exponential curve at the highest frequencies. You may remember that we already have a tuning mechanism in place for the exponential curve, and this uses a data input RP3. However, this mechanism, according to the specs, is able to adjust the lower part of the full range of the VCO only. To make sure that also the higher part of the range provides a good ratio of 1 volt per octave, we need to introduce an extra point of adjustments on pin 6 and 7. And this is done through this circuit that adds to the 267K resistor between those 2 pins an extra input that helps tuning the high range of the exponential scale. Once the VCO is finished, we will go together through all the tuning procedure, and so you will see how to deal with this new input and RP3. And finally, let's talk about the last circuit. The reason for it is to prevent the auxiliary inputs from getting a voltage higher than they can handle. And you can see from the schematic that these inputs receive directly what you put on them. But this is a fully patchable synthesizer, and so somebody can make a mistake and apply to the input the wrong signal, maybe one that is too high and would damage the SSI 2130. To prevent that from happening, we connect the auxiliary inputs to the output of 2 devices like this one, which will prevent the voltage on the pins to exceed 2.5 volts peak-to-peak. But how does it work? For a moment, pretend that the 2 LEDs toward the top are not there. Since the 2 resistors R1 and R2 have the same value, the circuit behaves like an amplifier with a gain of 1. The capacitor C1 is used to remove the possible DC component from the input signal, like in one of the 3 circuits we examined in the previous episode. Since the gain is 1, whatever we put at the input will be reflected on the output, with the same peak-to-peak value, but upside down, since this is an inverting amplifier. Everything works fine for very low voltages, and we can increase the input voltage up to 5 volts peak-to-peak safely, without causing the output to go beyond that value. However, if we input signals that exceed 5 volts peak-to-peak, we would find the same peak-to-peak signal on the output, and therefore on the auxiliary inputs of the SSI 2130, which we don't want. But now let's take a look at the effect introduced by the two LED. First, note that there are two of them. LED 1 is connected with the cathode on the left side. LED 2 is connected with the cathode on the right side. This means that depending on the polarity of the signal at the output of the operation amplifier, at any given time one LED is polarized directly and the other one is polarized inversely. And there will always be one diode that is directly polarized and the other one that is inversely polarized. That said, we can make our case working only on one of the two LEDs, and what we say will work also for the other one. Another thing we have to note is that the two LEDs are white. And why white? Well, because white LEDs have a forward voltage equal to exactly what we need, which is about 3.2 volts. Let's take a look at the IV characteristics of such an LED. The VF is the minimum voltage that we need to apply so that the LED can emit light, and we usually say that below this voltage the LED is off. However, as you can see from the diagram, even when the voltage is lower than VF, there is still a little current going through the LED, and the relation between this current and the voltage applied to the LED is exponential, as you can see. Do you see where I'm going? The LED on the negative feedback of the amplifier will work in this region, which I indicated with working area. Whenever the input and output voltage are very low, the voltage at the diode will be so low that the current will be negligible. But the more the voltage increases, the more the current increases too, and the negative feedback, initially set for gain of 1, will change, and the gain will become smaller. See, in practice the LED will work as a variable resistor, and the more the voltage, the smaller will be this resistor, and this will cause the gain to decrease with the voltage until no input voltage is amplified anymore. So, when the input voltage starts getting closer to our critical 2.5 volts, the LED will reduce more and more the gain of the amplifier until when we go over the 2.5 volts it will become almost zero. At that point the voltage of the output will stop increasing and will level up to the value of 2.5 volts both on the positive side, because of one LED, and on the negative side, because of the other LED. And so the maximum output will actually be of 5 volts peak to peak. This will happen, of course, at the expense of the shape of the input signal, which will be flattened out when we exceed those plus-minus 2.5 volts at the input. And that is how this circuit will prevent the voltage on the auxiliary inputs to grow over the 5 volts peak-to-peak value. Let's now move to the lab, and let's see how this circuit practically works. Here is the circuit mounted on a small breadboard. This is the op-amp, an LM358. These are the two resistors that set the gain for small signals to 1, and here are the two LEDs that are put in parallel with R2, but with opposite polarization between each other. And this is the input capacitor, which removes the DC component from the input signal. To test this circuit, I have connected its input to these two alligator clips that go through the cable to this function generator, currently emitting a triangular wave of 1 volt peak-to-peak at 800 Hz. I have chosen a triangular wave to begin with, because it has a rich content of harmonics, and we can better see what happens when the input signal voltage increases. We can see this signal on the second channel of the oscilloscope, which is the blue trace. The yellow trace, from channel 1, comes instead from this probe that is connected to the output of the voltage limiter, our circuit. On the right of the oscilloscope screen you can also see the peak-to-peak value of the two signals, which are currently almost identical. Blue is the input and yellow is the output. I will now increase the level of the input signal to see how the circuit behaves. Now we have an amplitude of 2 volts peak-to-peak at the input, and as expected the output has an amplitude almost identical, and the shape of the signal is unaffected. I am now increasing the input signal to 3 volts peak-to-peak, and the output, as you can see, is still fine. Remember that we should be like this until we hit the 5 volts peak-to-peak, only then we should start seeing differences. So now we are at 4 volts peak-to-peak. Let me adjust the scales of the oscilloscope so we can see both signals clearly. Okay, you see they have still an identical shape and almost identical amplitude. And now we are at 5 volts peak-to-peak, and things still look good, although you can see that the amplitude of the output signal has started falling behind, but just a little for now, and also the shape of the triangular wave is imperceptibly distorted, kind of vertically squeezed. Now look what happens when I increase the input voltage to 6 volts peak-to-peak. You see, the output amplitude is now falling behind and remaining around 5 volts peak-to-peak, while the edges of the triangular wave are now definitively rounded, since at that amplitude the amplifier does not provide gain anymore. And now, if I increase the input signal any further, the output amplitude does not change anymore, and the top of the triangular shape is more and more flattened out. And as soon as I lower the input, of course the output goes back to the correct shape. Let me show now the effect with another wave. Let's pick the sine wave. You see, so far the output is perfectly fine, but as soon as I increase the input and go past the 5 volts peak-to-peak, the output stops increasing after it reaches those 5.28 volts peak-to-peak. And the sine wave is flattened too, as you can see, exactly like the triangular wave. Let's now bring the input down one more time and let's experiment with a square wave. You see, the behavior is one more time the same, but when the input signal goes over 5 volts peak-to-peak, again the square wave amplitude does not increase anymore. Would you ever thought that a couple of LED could provide such a useful feature in an analog circuit? All these 3 circuits will be added to the whole schematic of the VCO, along with the ones from the previous episode. And that will complete the design of our featureful VCO. I'm really looking forward to build the whole module, install it into the Synth rack, and start experimenting with it to make some interesting sound. But this will be subject of the next few episodes of this series. So don't forget to subscribe and to click on the notification bell if you don't want to miss these episodes, and feel free to make a donation to help me run this channel. Links are in the description below. I'll see you in the next video, and as usual, happy experiments!